Ions and ionic bonds for Cambridge IGCSE Chemistry. Cambridge IGCSE requires knowledge of the type of chemical bonding, ion formation and bonding, dot and cross diagrams for ionic compounds, giant ionic lattices and their properties, and I would advise that you try the exam style review problems before moving on to another class. Predicting the type of chemical bonding in a compound relies on ideas on metals and non-metals. So metals are positioned to the left of the periodic table. Non-metals, except for hydrogen, are positioned to the right. The two types of element allow for three possible combinations. We can have metal and a non-metal, two non-metals, or a mixture of metals. We therefore need three different theories of bonding. Metal and non-metal bonds ionically, and that's the topic of this class. Two non-metals bond covalently, and metals mix and bond metallically. Ionic bonding involves ion formation and bonding between those ions. Ions are formed from atoms, the reacting atoms, by the loss or gain of outer shell electrons. So let's take an example: a sodium atom, a metal atom, and a fluorine atom, a non-metal atom, and look at the original electron configuration: 281 for sodium, 27 for fluorine. Now, metal atoms such as sodium lose electrons to form positively charged ions, which we call cations. So 281, the original electron configuration for the sodium atom, becomes 28. It's lost an outer shell electron. Consequently, it has become positively charged. The loss of the negative electron leads to the ion being positively charged. The non-metal atoms, for instance fluorine, gain electrons to form negatively charged ions. So by having additional electrons, they acquire a negative charge, and they are called anions. So fluorine starts off at 27, gains one electron from the outer shell of sodium to form 28, and therefore form a negative ion, the fluoride ion. Now notice the sodium ion and the fluoride ion. Their electron configurations are those of a noble gas, in fact of neon. So each element achieves a stable electron arrangement, a noble gas arrangement, by the transfer of their outer shell electrons. This may be referred to as achieving a full outer shell. So let's look at another example using the basic principles set out here. Sodium and chlorine going to form sodium chloride, a sodium ion, and a chlorine particle, 288. What is the electron configuration of the sodium ion, and what is the formula or the symbol and charge for the chlorine particle? Stop the class, identify A and B. Okay, so A, sodium has lost its outer shell electron to become 28. Chlorine was 287, now 288. So chlorine has gained one electron. It is negatively charged by 1. Let's have a look at another example. Magnesium and sulfur making magnesium sulfide. Can you identify C and D? Stop the class. Come back to check your answers when you are ready. Okay, so I'm going to reveal my answer. Magnesium 282 as an atom becomes 28 and a 2 positive ion. Sulfur was 286, has gained 2 electrons to go 288 and therefore has got a 2 negative charge. Note 288 is the same as the electron configuration of argon and the noble gas. So the process so far is that atoms are turned into ions, that is, charged particles. Those charged particles are positive or negative. These oppositely charged ions have strong electrostatic attractions between them. Opposite charges attract. And it's this strong attraction, electrostatic attraction between oppositely charged ions that constitute the ionic bond. Dot and cross diagrams. So electrons in shells can be represented by dots and by crosses. So let's look at the reaction between sodium and fluorine, which we've discussed before, to form sodium fluoride, a sodium ion positive and a fluoride ion negative. If we draw a dot and cross diagram for sodium, 281, and using crosses, for sodium and dots for the electrons of fluorine, then we can map where those electrons are in the ions that are formed. So sodium loses its outer shell electron, it's transferred to fluorine, which gains that electron. So sodium 28 in crosses, but we keep the notation of the cross for the sodium electron that has been added to the fluorine outer shell. So fluorine 27 over here becomes 28, but in the outer shell we've got 7 dots and 1 cross, so that we're tracking where the origin of that electron is. That is, it's come from the outer shell of sodium. Sodium loses 1 outer shell electron, fluorine gains 1 outer shell electron. Dot and cross diagrams gives us a way of tracking that transfer. So let's look at another example. Magnesium and oxygen making magnesium oxide, the magnesium 2+ ion, the oxide 2- ion. Here are the electron configurations or shell diagrams using crosses for magnesium electrons and dots for oxygen electrons for the atoms. Stop the class and draw the electron configuration for magnesium 2+ and for oxide 2- using dots and crosses. Come back to check against mine when you are ready. Okay, so magnesium loses the 2 outer shell electrons, so it becomes 2 and then 8 in the second shell. The third shell is now empty, so we don't draw it. The 2 electrons that were in the outer shell of magnesium have been transferred to oxygen to form the oxide ion. So we've got 6 dots in the outer shell of oxygen and 2 crosses. Notice the magnesium has become a 2+ ion. It's lost 2 electrons. Both outer shell electrons have been lost, so it becomes a 2 positive ion. The oxygen atom, neutral, gains 2 electrons, so it becomes 2 negative. What holds them together is, of course, strong electrostatic attractions, the ionic bond. As only outer shells electrons are involved in bonding, inner shells can be omitted from dot and cross diagrams, and we have what's called an outer shell only diagram. For example, forming calcium oxide. So calcium and oxygen, so calcium 2882 can just be represented outer shell only as a shell with 2. Oxygen 26, so we just draw 1 shell with 6 electrons, the outer shell only. The calcium ion 2 plus has lost the 2 electrons, so its outer shell is now empty. So we very often draw an empty outer shell and put 2 plus clearly alongside the calcium particle. So that's a calcium 2 plus ion. The oxygen had 6 electrons in its outer shell. It's now acquired 2, so we can clearly see that in the outer shell diagram, and the oxide ion obviously 2 minus. So outer shell only diagrams omit the inner shells for clarity and for speed. Giant ionic lattices and their properties. As solids, ionic compounds form regular arrangements of alternating oppositely charged ions. We call this a giant ionic lattice. In 2 dimensions, we've got positive ions surrounded by negative ions in all directions. We have negative ions surrounded by positive ions in all directions. These ions are held by strong electrostatic attractions that work in all directions. So attractions to the right, as I'm reading it, attractions to the left, above and below, attractions in all directions. You'll also see 3-dimensional representations where we have a positive ion with negative ions to the right and to the left and behind and below, and of course a negative ion with positive ions to the right, to the left, above, below, behind, and of course I haven't drawn them, but they would be in front as well. So you'll see this 3D visualization with the ions as solid spheres. Or common in exams or in textbooks, 3D ball and stick models. So we have a central positive ion, a negative ion to the right, to the left, above and below, behind and in front. And of course, this is a small section of a giant structure which goes on for many, many millions upon millions of ions in all directions. You are expected to know the distinctive properties of ionic lattices and to be able to explain them. So we have, as a solid, a giant lattice of oppositely charged ions. If we heat it, it will become a liquid, that is, it will become a molten compound. To achieve that, many ionic bonds have to be broken. Those bonds are strong, and therefore a large amount of energy is required. And that explains the melting points of ionic compounds being at a high temperature. Ionic compounds are soluble in water, that is, they dissolve. So we might write that as an equation as solid sodium chloride and water going to form what we will call free aqueous ions. So here is the solid with the giant ionic lattice, sodium and chloride ions held rigidly in place. This lattice is broken down by the action of water. The ions become free and aqueous, that is, they can move independently of each other. So the sodium ion can move around independently of the chloride ions, and the chloride ions move freely throughout the water, independent of the sodium ions. The key point is that the ions are now free to move. Here, the ions are fixed in position. Here, the ions are now free to move. A further property of ionic compounds is that they are electrolytes. That is, they conduct electricity when molten or in solution. So a molten compound, a voltage is applied, a current will flow. Similarly for a dissolved ionic compound. But ionic compounds, electrolytes, will not conduct as solids. to this combination of conduction when molten or in solution and non-conduction as a solid meets the description of an electrolyte. Now, the positive ions move to the negative electrode. So if we have a positive ion, that will move to the negative electrode. If we have negative ions, of course we will, the negative ions will move to the positive electrode. Opposite charges attract, a very simple principle. It is the ions in the electrolyte that carry charge. Electrons carry charge in wires, but within an electrolyte, it is mobile ions that carry the charge. And that explains why ionic compounds are non-conductors as solid, because of course, in a giant ionic lattice, the ions are in fixed positions and are not able to move. I would recommend that you now attempt some exam-style problems as a way of checking your learning. Predict the substances which would show ionic bonding. Stop the class, make your choices, come back to check. Okay. Magnesium is a metal, oxygen is a non-metal. We would predict ionic bonding. Sodium is a metal, bromine is a non-metal. We would predict ionic bonding. None of the others are combinations of metals and non-metals. Identify the ion and the electron configurations for A, B, C, and D. Stop the class, come back when you are ready. Okay, so I'm going to reveal. So calcium becomes calcium 2 plus 288, and oxygen becomes oxide 2,8. Fluorine becomes fluoride. Lithium becomes from 2,1, it becomes 2, and fluorine 2,8. Complete dot and cross diagrams for forming these two ionic compounds, sodium oxide and magnesium chloride. You have the atoms on the left. Can you do dot and cross diagrams for the ions that are formed? Stop the class, draw your shell diagrams, and dot and cross diagrams, come back to check. Okay, so to reveal, we've got two sodium ions. Each sodium atom loses one electron each, so each sodium becomes one positive. Oxygen has gained an electron from two separate sodium ions, so we've got two additional crosses in the outer shell for oxygen. It's gained 2 electrons, so it is 2 minus. Now, if you didn't get that right, perhaps go back and check your work for magnesium chloride. Otherwise, I'm going to reveal now. So magnesium has got 2 electrons in its outer shell. It loses them both to form a 2 plus ion. It's the metal, so it loses its outer shell electrons. Chlorine, as an atom, has 7 electrons. It needs to gain 1, so we need 2 chlorides to be formed, each chlorine accepting 1 additional electron, as indicated by the dot and cross diagram. The magnesium is a 2 plus ion, but we have 2 separate chloride ions at 1 minus each. Last question, select the correct statements about the properties of ionic compounds. So you've got 5 statements, each statement has a number. Select the numbers for the correct statements about the properties of ionic compounds. Stop, restart when you are ready. Okay, so I'm going to reveal the answers. The correct statements are 2, 4, and 5. Ionic compounds have high melting points. They are good electrical conductors when molten. They are soluble in water, so statement 3 is false. Conductor aqueous solutions, that's true, as is the statement. Ionic compounds are non-conductors as solids. So 2, 4 and 5 are correct statements. So well done for finishing. If you want more practice, which I would advise, use your textbook questions first, then find past paper questions. If you haven't come across Physics and Maths Tutor website, I would recommend it. Nothing to do with me, it's just got loads and loads of past papers. For more related chemistry classes, look at the playlist or the links in this video description. If you found this class helpful, please recommend it to a friend. Subscribe for new classes and last-minute exam tips. Please like.